here. All right. So they focus on a lot of fuses, guys, and so forth. So I'm going to go and show you the videos. This is an arc flash inside a box. I'm sure some of you guys have probably seen that. So three-phase arc flash inside the box. So it's open. When you go, anybody have seen that, guys? It's in slow motion. When you go to NEC2011, and they talk about arc flash boundaries, the two types of arc flash boundaries calculation. One is based on a box. That's what's based on a box. You are standing in front of a panel. The door is open. You're completely exposed to the hot energized objects, and you accidentally grounded one phase with one of your tools. What you get is you get an arc flash, what we call it an arc flash, high impedance flash. And with arc flash calculation, that's based on an open, because it's in a box. It's going to channel all this energy right through your tummy, or my tummy, right? So that's the worst that could happen. That's inside the box. If it's not inside the box, guys, would be another arc flash that could happen is, say you're working on an open wires. There is no box, right? And you accidentally grounded phase to the pole, which happened to be a metal. Now they will have an arc flash, but there's no, it's not a box calculation. So instead of channeling the energy right through your tummy, the energy will go all over. So which one is the worst, you think? Box. So that's why a lot of calculation that we do in 70 is based on the box. Okay, here you get to the box. So so that's the first arc flash, just to emphasize. When it comes to arc flash, guys, 70E and OSHA emphasize the shock hazard. There are two hazards come out of electricity. One is the shock hazard. Most of us, especially the older we get smarter not to touch energized objects, right? Especially the older we get. So the shock hazard is typically, we're good at avoiding the shock hazard. What we haven't been good at is avoiding the arc flash hazard. The arc flash hazard, you're working on a switchgear or panel, you drop the wrench, you drop the any metallic object, it arcs, big ball of fire comes, and you are not dressed up for it, you burn your face. The arc flash hazard, guys, and the shock hazard is a function of very, very important three aspects. Voltage is extremely important when it comes to shock hazard or arc hazard. So if you get a shock with a 24 volt, it's completely different than if you get a shock from a 2400 volt, right? So higher the voltage, the more energy the voltage can push right through you, either as a shock or as a big ball of fire to engulf you. That's why a 480-277 shock arc flash is extremely more dangerous than a 28120, because it can pushes more energy into you as a shock hazard, or engulf you with bigger, more destructive ball that's full of bullets and melted copper to engulf you, right? Isn't that what the arc flash is? And so that's number one. And over this, we have no control over the voltage. Most of the time, guys, you walk into a switch gear, the voltage has been determined that we're going to run equipment at 480-277 or 28120. We have to deal with what we have. The second part that guys make a major part is the overcurrent protection device ahead of them. So if you have an overcurrent protection, first of all, if the overcurrent protection device is not sized right, if you have a ground fault or an arc flash, a ground fault or a bolted short circuit, the circuit breaker will not have two options for circuit breakers. Either it melted together and it acts like a conductor and it wouldn't open, or it will explode, right? Because it can't handle it. That's because somebody screwed up and did not size the circuit breaker to handle the so-called available short circuit. The second thing, guys, that could happen is your circuit breaker also can allow this amount of energy. If you have an arc flash or short circuit, this amount of energy is allowed to push right through you, either engulf you in a ball of fire or right through your body if it's shock hazard, this amount of energy for this amount of time, right? The energy is based on time and power. Now, if you put a fuse, a current limiting fuse, that's what Busman becomes big deal on them. When you put a fuse, what the fuse does is they open so fast that instead of this amount of energy engulfing you or pushing through your chest, it will become this amount of energy, right? And by minimizing the amount of time exposure. So who cares? Your chances of going home with your eyes is much higher, right? Instead of leaving it behind you. Is that graphic? We're leaving a finger there. So that's the whole idea. So look at this cable, guys. When we have a short circuit condition, since we're talking about overcurrent protection device, when you have a short circuit condition, there are two forces act up on the equipment or the circuit breaker. Force number one is heat, right? So you have current, voltage, here's energy, multiplied by time becomes energy, right? Power, volt times current multiplied by the time in seconds, typically in seconds, thanks God. If it's in hours, you're done, or minutes. So this amount of energy, right? So this amount of energy is going to act up on your switch gear. It's going to cook your switch gear. So if you have a short circuit, I always say if you have a short circuit condition, your switch gear, inside the switch gear or panel, your equipment is being cooked, literally cooked by the heat that's coming out of the voltage and the current. The cooked is one thing, and I call it shake and bake. It being baked by this equipment and also shaked because you have a magnetic force, right? The peak, if you guys are familiar with the short circuit, the peak of the wave contribute to the shake of the equipment. So you have a magnetic force shaking your equipment if you have a short circuit. So you have a switch gear short circuit, three-phase or ground fault. You have two forces. One force, your switch gear is being shaken, and if that's not enough, also it's being baked by the heat. So you can imagine what you just is going to happen to your equipment. So to minimize the shaking and the baking, what do? We put the proper size of the overcurrent protection device. The proper size, guys, will open the circuit breaker fast enough to minimize the shaking and the baking of the equipment. So that's to protect the equipment. To protect the people, we also shield you and me inside the switch gear from that energy. That's why the panels are always closed. If there's a short circuit, they act and they interrupt the short circuit without exposing us to the hazard. The problem becomes if there's a short circuit or ground fault while we're working on the equipment. And that's where OSHA comes in 70E and it says we usually have to put the proper PPE before you work on the equipment as an exception, not the rule. The rule is you work the energize. The exception is you work on the equipment energize if you have a reason. As I said, an inconvenience is not a reason. So take this. Have anybody seen these videos, guys? Did you see the cable? Okay, is it the same? Okay, let me show you the overcurrent protection device, the cable here. Did you guys see it? Okay, it amazes me how do you guys now understand why when we put conductors, we put them in a conduit? Why can't we just let them loose there? That's number one. And number two, do you understand when we put them in cables, why we stable the cable, right? Stable our cables. That will give you a major understanding why we stable, because that's a magnetic force and the heat that cuts this thing into pieces. So did he show you the other one? So that's no overcurrent protection, no proper overcurrent protection device. Did he show you that one? Did he show you the second? I'm sure he showed you the second one. There's a low peak. Here's, of course, done by busman. So what do you think busman is going to do? Yeah, try to get you into. So you can see that there's a gump. You see there is a magnetic force. Could you see that magnetic force that acted on them? And there is heat, but the heat was minimized. The magnetic force was minimized. No hurt. No, everybody goes home safe. So anyway, I like to do this one because it emphasizes the proper overcurrent protection device, number one, and why we put things in conduits or cables, and why do we stable the cables and the conduit by the code. Does that make sense? So he showed you that. Did you guys show you the explosion, and did he show you the other ones? I don't know if he showed you this. Okay. Did you see that one? Okay, now this is, let me just, okay, here. So this is what happened if, here's what this, did he tell you, did you guys see that? Okay. This happens if The available short circuit inside your switchgear, you calculate it, and you came up with 65,000 amps. So if I grab phase A to B to C with a big piece of cover, bolt them together, and send my electrician, my apprentice, to flip the switch on and go home. That's brutal. That's what could happen, right? Now, if that's to happen, say you calculated 65,000 amps is what could the potential short circuit amount of short circuit inside your switchgear. When you size your circuit breakers have to be sized to interrupt 65,000 amp or higher. So now if you put 55, that's what happened. If you put a 55,000 amp interrupting rating circuit breaker on a system that rated, here's 55, and here's the 65, the available short circuit. So the fuse sits there and sees a huge amount of energy, and because fuses are so stupid, instead of raising their hands and say, I can't fight, they pick the fight. And this is what happened when they pick the fight. They turn into a big fuses or circuit breaker. Now, there's nothing wrong with this if this is behind closed panels. If the door is open or you're standing right in front of the door, all this energy, melted copper, all these pieces that's flying up in the air is right through your chest or my chest, right?
Again, this is a serious misapplication.
So that's what we call it, the misapplication of circuit. This is a circuit breaker. The same thing could happen to a fuse, misapplication. So, and they expedite the whole thing here, guys, to slow motion so you can see it. Look at that. Can you see the fuse? In a case like this, the fuse should have sat there and raised his hand and said, I can't fight. This is a fight that I can't pick. They pick a fight and they die in the process.
This is a serious misapplication.
Well, apparently, right? So that's kind of the start of the fuse and circuit breakers. So when you have a fuse and circuit breaker, the single most important thing is the available short circuit. You have to do a short circuit calculation. I'm going to take you guys, I'm going to make the unorthodox way of doing this class. Because of the time, I'll show you a couple of things. So, have I convinced you guys the misapplication? Everybody can see the misapplication. Let me show you how do we do the misapplication for circuit breakers. I do have a software here that I always use. It's called SKM. Anybody have used SKM? You guys have a bunch of engineers. You're familiar with SKM. So when you go on SKM, I want to take you directly to how do we size the circuit breakers. Well, guys, we're all smart. If I ask you, I told you, I have a machine, continuous machine, size me a circuit breaker, Chad, and it's 100 amp. No problem. The code says continuous machines, guys, have to be sized based on 1.25. Take the 100 amp, multiply it by 1.25, they'll give me 125 amp, and I stick 125 amp circuit breaker right ahead of it, right? And I size the cable to match the 100 amp. Done. That's the normal operating condition for the circuit breakers. That's under normal operating condition, the circuit breaker have to handle 125 amp. Under abnormal conditions, your circuit breaker have to handle the short circuit and the ground fault. And let me go into, okay, where did they go here? Right view. Okay, so it went down a little bit. Where did my equipment? To the left? Where's my zoom? Okay, here, zoom. There you go. That's my print. Where's my zoom? Oh, here you go. I zoom off. I was looking for these. Here you go. Zoom off. So when we have a circuit breakers, the circuit breaker have to have actually have to have three things before you or fuse. You have to have three things about circuit breaker or fuse. Number one is the voltage. Is the system 480? Then typically we either buy a 480 circuit breaker or fuse or 600 volt. 600 volt can handle 480. The voltage. So if you put a circuit breaker on a voltage that's higher than what that circuit breaker can handle, you will expose him or her, if the circuit breaker is him or her, into more stress and they will malfunction. So that's the voltage. The second thing is the trip, they call it long time pickup for the circuit breakers. That's if you have 100 amp continuous load multiplied by 1.25, you get your 125 amp. Here's a 125 amp circuit breaker. Done, check. That's the second thing for a circuit breaker, voltage and current. A lot of us guys are very familiar with this. The third thing is the interrupting rating. And that's what a lot of electricians probably don't interfere too much with the interrupting rating. The interrupting rating, if you have, that's a short circuit and ground fault condition. If you have a short circuit, how much current can this circuit breaker handle before it turns into pieces, like you have seen? That one becomes a big deal. So let me just walk you guys through this system, very little system here. Let me zoom in here. Okay. Or maybe zoom all and see what we can. Okay, if you, I don't know how much you guys can see, this is software that we do short circuit analysis on. Starting right at the top here is Excel Energy, and it could be Minnesota Power. We pick on Excel because we're in the cities. Coming here, the transformer that I showed you when we were doing that bonding and grounding, we grab our cables directly here into what happened to be, this is a meter, we're simulating the utility here. So right here, when you go to short circuit calculation, I'm giving you some material to do by hand. You're going to tell Excel, call Excel and say, hey, I'm in at this location. Can you guys tell me what's the available short circuit right at this location of your distribution system? So you have to use Excel's number. If you don't have Excel's number, then we use what we call it the infinite source. The infinite source is based on the transformer that they give you, 500 kVA. Find the full load current of the transformer of 500 kVA, easy. What's the voltage at 480? Divided by the voltage, 1.73, and then divide it by the impedance of the transformer, which is typically from 3 to 6%. And you get yourself what? The available short circuit, the worst scenario available short circuit. That's called the infinite source. The reason why we call Excel most of the time, because you get lower than that number. And if you Excel engineers, you guys work for Excel, well, you call them many times, you call the engineers based on your location in the distribution line. They have their own calculation, and they tell you the available short circuit right at this location is 23,000 amp at the right voltage, which is 482.77. Or we did them in the medium voltage at 13.8. They have to give you the voltage as well as the available fault current. So that's here. Then I pull my cables. Here's my cables between them all the way. This is my meter cabinet. Into this system, guys, happen to have an auto transfer switch with a generator here. The system that we have. So here's my gen. I have my cables coming to a circuit breaker, 2 circuit breakers. This is my service for the utility. This is my disconnect for the generator. Through an auto transfer switch down to my panel. Very simple system. Very simple system. In a case like this, I don't know how many people have done an auto transfer switch that's rated for service entrance. They sell them. You have to have 2 circuit breakers, basically an auto transfer switch, or they use 2 circuit breakers as the auto transfer switch. Okay, so we came over here, and then all these are impedances into the system down into my equipment right at the bottom here and my bunch of panels here. So who cares? Let me just show you. When we click on one of these, here's what you get. This is the source of all evils, how much energy is going to push through your system. And this one happened to be, for our example, 50,000 volt at this location. So these 2 numbers, typically we get them from the utilities. That's the available short circuit. What does that mean? Meaning, if you take phase A to phase B to phase C, right at the secondary terminal of Excel transformer, right at this location, downtown Minneapolis, for example, and you flip the switch, that's how much the distribution system of Excel is going to push right through your building. As a short circuit, 3-phase, and as a ground fault, typically the ground fault is lower half of that value. And the impedance of your system, we're not going to get into that one. So that's your source that you get when you do the short circuit calculation. The short circuit calculation. Then when you get out of here, and then you get, let me just grab, see how the system works. And I don't want to make you guys SKM. Here's my cables I'm using. I'm using 250. I believe this was a 600 amp panel. 250 KCM, 2 runs of them, 3 phase. And the conductors that I'm using is based on IEEE, now IEEE again, books. We have copper, non-magnetic, so we're coming with PVC conduit. And we're using THWN and rated for 600 volt, and I'm using 4 single conductor cables in a conduit. And I'm running 50 feet into the termination box. Cool? From the transformer into the termination. That's where you put the distance. Who cares about the distance? I'll give you the impedance. Okay, I'm showing you this one because when I show you the calculation, so that's coming here. I'm going to go back, guys, into chiller here and show you how you model the system. Oops, zoom all and model your system here. Okay, here's my cooling unit. I have a cooling unit here. My cooling unit here, guys, happen to be a 16,000 kVA. Here's the power factor for it. And then you model all your equipment. The reason why you model all your equipment, as you guys familiar, if you have what happened to the motors if you have a short circuit in your building? Thank you. You turn in, absolutely, momentarily, all your rotating equipments, anything that rotates momentarily, they turn into, instead of sucking current and power out of the system, into pushing power into the short circuit connection. So they will be they'll contribute to the value of the short circuit. Who cares? So now you have Excel pushing current into the short circuit, and all your air handling units, chillers, rooftop units, exhaust fans, all of these rotating equipment also pushing current typically equivalent to their start locked rotor current. Their locked rotor current. That's the kind of the rule of thumb that we do. So if a motor is a 100 amp motor, and say roughly 6 times this is the locked rotor current or the start current, they will be pushing under short circuit condition 600 amps into that point of short circuit. So they contribute to the short circuit. Okay, so when you do that, my friends, let me do that one. And then I'm just going to take you to run. Here's your run balance 3-phase circuit. And this is how you run load flow short circuit right here. Every system, so you put the impedance. Here's as easy as doing the calculation for you. You guys are supposed to do it by hand. I have a handout for you. So now my short circuit calculation is done. See how nice? The nice thing about, well, the not nice things about this system is this costs all the modules close to 50 grams. If you want to buy all the modules, that's harmonic analysis, starting motors. But you can buy probably for maybe $8,000. You can do most of what you need, 80% of what you need. Anyway, so let me just go show you really interesting stuff. Let me show you the calculation, the short circuit, because it's directly related. Okay, so I'm going to go document. Actually, they're here. Here's my document and text. And here's the short circuit report that you get. Okay, now after you did all this, I'm going to go all the way down to the bottom. Okay, here's the single most important. So when it calculates based on impedance, you're getting at so available short circuit. See, guys, available fault current, line to line voltage, 3-phase, line to ground, right? So let's go to bus main panel. MP is main panel. It's a 2-8 system. Here's how much current available of this 1 to 3. As a 3-phase, here's my ground fault 13.6. The RP is receptacle panel for us. LP is a lining panel. So the lining panel is a little bit further away, so it's 17.8. MC, can you guys remember the MC? That's meter cabinet, right at the beginning, right? At the meter cabinet, look at the value, 32. The meter cabinet, there's no circuit breaker. It's ahead of the main. So if you were to open this one, you have 32,000. And here's your ground fault. Okay, who cares? Now, my main panel, if my available short circuit 23, and I went and I installed the 10,000 amp interrupting rating circuit breakers. What you saw in the video, when the circuit breaker exploded, that's exactly what's going to happen. So when I go size, guys, the short circuit right now for this circuit breaker here, the main, it has to be 30 in this case right here. It's going to be 23 or more, so it's going to be probably 35. I don't know if they make 25, 35, say 35,000 amp interrupting rate. So you have a short circuit, the circuit breaker say up, I can handle it, open, and everybody's happy. Any comment, guys, about this short circuit calculation?
You don't have a calculation of transfers.
Well, because I did not, you have to assign the points that you want. I just didn't assign a point.
Okay.
You can find the available fault current at any point. That's what the B is. The B is telling the system, I care about the point here. I just told the system at the time I didn't care about the point here. But you can imagine at the auto transfer switch, there's a circuit breaker ahead of it. So I can predict it's going to be around the MP 23 or so because there's a circuit breaker ahead of it. Okay, this is not the exciting stuff. The exciting stuff is going here. Now, before I take you guys there, here's my available fault. Here's the coordination. I have my circuit breakers here, and I have a bunch of circuit breakers here. If I have a short circuit right into this air handling unit, which circuit breaker do you want to trip?
The one in front of it.
The one in front of it. What does that call? Overcurrent protection coordination, selectivity, required on hospitals, for example, is required. Emergency system is required. Okay, so how do you do that? And that's part of our presentation today. Let's go to, I have main panel air handling units right here. So if you look at this, you get these beautiful fancy circuit breakers. The first circuit breaker, guys, right here, this is circuit breaker MP. That's the main circuit breaker for the panel. Can you guys see that green one? The second, the black one here, is the circuit breaker that protects the air handling unit. That brown cable here, the brown wire here, is the starting curve of the air handling unit. So when you flip the switch on the air handling unit or push the button, the air handling unit is going to have an rush, right? So from here, from this value here, air rush, it's going to go up, 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 almost 10 seconds. It's going to be pulling 6 times more current, and then it goes back to stable and runs forever at this value. So if you guys look at the green and the black, are they touching each other? The only place they're touching each other right here, slightly right here, they're fully coordinating. So if I have a short circuit anywhere from this point all the way down in the air handling unit, I'm guaranteed that the only circuit breaker that's going to trip is the circuit breaker ahead of the air handling unit, not the main. So everybody's happy, right? You don't want to trip the main every time. So that's so the rating of this. Let me just look at the setting. Here's my circuit breaker here that I'm dealing with. This happened to be a 24 volt circuit breaker, 150. The interrupting rating of this circuit breaker, can you guys see that? 42 kiloamp. And what was the available in my system? Do you guys remember that? 20, was it 23? So we're good. The available at that panel, we're good. Here's the trip plug. It is 125 amp. So right here is 125 amp. Right here, can you guys see that edge here? That one, how much? 42,000 amps. So right at this point here, this guy can handle up to 42 kiloamps. 42 kiloamps. Up to 42 kiloamps. Okay, so that's basically what it is. I have the conductor here. I don't know if you can see the conductor here. That's called, later on when I show you a couple of slides. So now how do you adjust this? Can you guys see that? Look how easy that. Now I have just raised, just by that movement, raised my PPE when I work on this piece of equipment from category 2 into category 4. Just by that flip. This is your instantaneous. Can you guys see that? Now I want you to watch right here, instantaneous. Now it's set at high. It's set at high says if I have a short circuit condition right here, right here, don't trip, don't trip, don't trip, don't trip, don't trip, and allow it to sit like, what is it? These are 20 at 20 seconds. Wait 20 seconds before you trip. So now you're standing in front of a switchgear with an arc flash, and the circuit breaker is waiting for 20 seconds before it opens. You're exposed to 20 seconds of energy. Okay? Now, how do you minimize this? And no need for this. I mean, No need to push it all the way because I just want to make the air handling unit start so I can push it back. Too low, right? So all the way. Now, if I have a short circuit right here, instantly my circuit breaker will trip. And that's what you want. Otherwise, you expose your people to what? A huge amount of arc flash. Anyway, so that's what we call, guys, the coordination. You need to coordinate between the main and the feeders, as well as the equipment that's protected by the feeders, as well as the equipment that's protected by the feeders. So, and that's as easy as, I don't know if you can see the instantaneous here. You can set it at 2. Can you guys see how it moves? You can set it at 3. You're familiar with adjustable circuit breaker instantaneous with a screwdriver. You can set it at 5, or you can set it at high. And the more you go to the, where are we going? To the right here, the more energy you're allowing to sit in your equipment, right? So that's what the overcurrent protection coordination will mean. Any comments, guys? Any questions about this? So when you pick a circuit breaker, you're going to pick the circuit breaker based on the trip unit, the trip value, which is that value right here, and the short circuit, the high short circuit here, to match the available short circuit to your system. So let me change this circuit breaker, guys, into a different circuit breaker if I can. Here's my options in this series. And my option is I can go 110. Look how it's going to shift to the left here if I put 110. Can you guys see it move to the left? Now with one click, I moved this circuit breaker from 125 amp into 110 amp. You can see the whole curve shift to the left here. If I want to make it bigger, I can make it bigger and shift it all the way. That's your trip. In most of the application, what I did right here, guys, is that will be a completely different circuit breaker for this type of for this series. And look how, if I move it this way, how high I can move. Look at the amount of energy now I'm allowing to stay if I have ground fault in my chiller. I hope what I'm trying to get into, guys, the lower setting for the instantaneous, the more protection you have for you and your people when you're working energized. Cool. So that's one curve. I'm going to show you what you end up doing in terms of when you get the report, and I'm sure a lot of you guys have done these reports. Let me just tell you here's a report that we will look at and you get air handling unit. Here's what you get from the engineers, unless you are the engineer doing it. You get into, okay, so this is circuit breaker, report to it, bus phase, square D, LC. Okay, here's what you're going to get. Here's the circuit breaker that we're using. This is a square D circuit breaker. It's description between these 2 amps. Arc interrupting, that's the main. That's my main one. The main is rated for this amount. Here's the voltage. Here's what it's set for, 500 amp. This is the trip 500 amp. It's thermal curve, and it's set, the instantaneous is sitting right now at the high. So it will trip at 5,000 amp. So when you guys get this report, what do? You go to the front of the transformer, tweak, and we tweak the circuit breaker to either high or low or somewhere in between. Okay, so that's basically the overcurrent protection device. Let me show you how this impacts your arc flash, right? Let's go to the arc flash. So directly into my arc flash analysis. Here's my arc flash analysis, just to give you an idea. When you go to the arc flash, the software allows you to use IEEE 1584. That's the most common one. You can also use NEC2011. Does that sound familiar to you? That's the book that we're holding right here. You can use the tables in this book to size 70. That's the label, arc flash label. You can see them. Or you can use these two, NEC2012. That's a utility type or DC system. So we're using the preferred one. So you go down here and you do arc flash, and you get yourself this calculation. Let me go to the labels because you guys are very familiar with the labels and preview. Here's all the labels that I'm going to do. And gentlemen, here's the labels that you can generate, arc flash labels for that system. Can you see the red one, guys? What does it say? No safety PPE exists. And that happened at which switch gear? BMC. That's happening at arc flash. This is arc flash. So the MC, not short circuit, it was 32. The short circuit was 32. It was not a big deal. There is no circuit breaker ahead of it. I did not put circuit breaker ahead of it because the utility owned the transformers, and typically they put their circuit breakers on the primary side. So I assume there is no circuit breaker here. Then this means if you are to work in the MCC, you better de-energize the equipment because there is no circuit breaker that can protect you from arc flash. From arc flash.
What's the calories on that one?
Let me
On the table.
zoom into it. Here you go. So the calories is 65, and category 4 can go up to 40. They make 100, I believe, but they're not recognized by 70.
We kind of say over 40, you can't work on it energized.
That's exactly
the blast will kill you.
Yeah, because there are two things, right? There is the arc flash engulfed in the ball of fire, and then there's the pressure and the blast that's going to kill it. So that's 65. Look at the arc flash boundary, guys. Flash boundary is 17 feet. And the reason for this, because there's no fuse to protect me. This is the meter socket. We're talking about the meter socket here. For a 500 amp, for a 500 amp 2.8, it's a 2, even in a 2.8. There is no circuit breaker ahead of it. Now, if there is a fuse or a circuit breaker ahead of it, it will knock it down to a lower value. If you guys look at this one, this is RP for the receptacle panel. My arc flash boundary is 8 inches. Level 0, cotton shirts, glasses. You don't even need a shield for category 0, right? No shield. The limited, you're familiar with limited approach, restricted approach, and prohibited approach. These are the touch hazards. So limited approach is 3.6. Restricted approach, prohibited approach is the tools. So just don't touch. This is 2.8, remember. If it was 480, usually the prohibited approach is a couple of inches. And the restricted approach is for your chest. When you're standing here, how close you can get. Limited approach is for people, if you're walking around the switchgear, non-authorized people can walk through the limited approach, but they have to be supervised. You guys do training, right? 73, and we talk about the limited and prohibited and restricted. Okay, so that's what the label that you can get out of this, the labels that you can get out of this system. Any comments, guys? Any questions? So I showed you the high end of it. Now we can go to doing it by hand. How about that? No, thank you, Chad. You guys signed for an Overcurrent Protection class. You could have signed for a dancing class or singing one. It's not approved. It's not approved by the code. Okay, so that's basically what I want to. So that's my arc flash. So I thought to show you guys, not bragging or anything. A lot of people guys do that. So you start by you building your one-line diagram from the component. You run short circuit analysis. It gives you what the short circuit level in every switch gear or panel, and then it gives you labels too. The arc flash label that you can stick right into your panel. How do you guys use your own now? Everybody use a scam? A lot of people use it or different. The manufacturer will label it. Okay.
Yeah, they'll label it, but they'll do this. Right now, the engineers throw that short circuit study back on us.
Yeah.
As part of the spec, and it costs us about a really good sized job. It'll cost us 15 to 20 grand.
Yeah.
Short circuit study coordination.
Yeah, yeah. All the engineers' jobs that we did, the engineered jobs, they're all come up with an arc flash analysis, short circuit analysis, and ground fault, and coordination. So that's okay. So that's what I wanted to show you guys before we get into it. So that's kind of the high end of that.
If you go through and do model your system, and you got all the impedances and your arc flash calculations, you generate all the labels, you stick them on your equipment, and now you just add to your system like you're paralleling off I guess you gotta run the numbers again, but these numbers probably won't change that much anymore.
Okay.
Yes.
Yes. In 2011, that was in 2011. Every service, everybody knows the change in 2011. Every service must have the available short circuit. What I showed you guys at the 23, that has to be stamped right at the service entrance equipment only, not the sub panels. And if you do a substantial amount of change, you have to recalculate and relabel. And based on OSHA 70E, that's NEC2011. Anybody knows what 70E says? If you don't even add to your system, every 5 years you have to recalculate. Anybody, you're familiar with that? Every 5 years, 70E says the short circuit availability, you have to recalculate every 5 years, regardless if you add or you don't. That was changed in 2012.
I just wonder, like, if you did an arc flash analysis and this label calls for category 2, 7 calories or something like that. Now you make a slight change and it's 7.1 or something like that. I mean, you know, how do you manage relabeling everything, or if it's still maybe the same category? I wonder if you could, I suppose you could pencil it in, you know?
Well,
That's a big job to relabel.
yeah. Well, what we do, if what we did, guys, but again, I know it's expensive. What we did as an engineers, we keep all this data. So if the job is engineered, piece of cake. You call the engineer and say, oh, by the way, we're adding a chiller. What size chiller you guys are having? It's going to be a 200-ton chiller. Or we're adding an exhaust fan, 15 horsepower, right? All what I do right now is I go back into my system, and it really doesn't take much. So you want to add a chiller, a motor, no problem. Here's my motor. See how easy that is. And here's my cable. See how, and I'm going to attach my cable here. And where's your circuit breaker? And where's my circuit breaker? Here. And here you go. Here's your system. And now all we have to do is just tie him, pick up the right conductor here. Literally, it will take me 10 minutes to add any single load to that diagram and give you the relabels. And tell you if you have to relabel, but I'm going to rerun it. And it will tell you, it might be the same labels. I'll send it to you. Well, you usually have the data. You compare them. If it's the same labels, just you keep it on record and you say we calculate and we don't need to relabel. See how easy that is? Right? 10 minutes. Now. Well.
10 hours later.
Do you see how well you know how that goes. You go. You have to do what?
Temporary labels on before we the final commissioning.
Okay. And permanent. You redo it twice. Yeah. After the same thing. Okay. So that's basically what the calculation is. For in your case, you call the manufacturer and say, I don't know if they're your friends, they run it for you.
Well, you know, you talk to the engineers, they say, well, we don't know what you're buying. So they want the manufacturer to do it, and sometimes they'll have eaten it.
Any engineer that tells you what you're not buying, that they don't know, I'm sorry to say it, but
I know, I'm just saying.
I know, I hear you. Because when we did the analysis, when we did hospitals, before we even bought the system, I go and pick up Square D or collar hammer circuit breakers and run my study of collar hammer, but the worst scenario. When we get the equipment, like you said, we know who the manufacturer is. It will literally take me 1/10 of the time to go flip the circuit breaker type from this manufacturer, and rerun the system. Everything is set. So really, there's defaults. And I don't know what wiring method you're going to use, MC cable. Well, I assume if you're going underground, PVC conduit, right? And conductor. That you do is a lot of assumption, and then you change it later on. You see what I mean? But I hear you. So that's the calculation. Any comments, guys? Any questions about that?
You don't have to do it twice, so you can size the circuit breaker approximately right the first time anyway.
Yeah. Well, what we do, guys, when at least the engineer jobs, the owner wants an approximate price, right? That's what happens is they come to us as an engineer and say, what size cables what size major equipment you want? So we run our calculation for this hospital. We come up with a 4,000 amp switch gear and 85,000 amp interrupting rating main and a couple of MCCs here and there, and that kind of the big picture. And typically, if you have done it before, you are off by 10 to 20%. If you're in this, really not a whole lot. I did wastewater treatment plants, and I remember after you do a few of them, either you're dealing with a typically 800 amp MCC service or 1600 MCC service. Really, typically most of them are the same. And then I used to ask the wastewater treatment plants, I said, before you even, I know what the material is, tell me how many aerators you guys have. That's how many clarifiers. That's it's not even a load. Clarifiers you're going to have and ditch aerators and all stuff. Give me the aerators. From the aerator, I can give you a size. Because you do it so many times and you accumulate the knowledge. So, but you have to do it a few times before. But then you do the details so you can kind of cover your butt. Right? Any comments, guys? Any questions about this? Now, you guys don't have the chance to do it by hand, by your software. So what I'm going to have for you here, I have, if you guys take one and cast, I have a short circuit calculation done by hand as part of what you're going to be doing, guys. Okay, I'll wait until you guys reach that one and I'll go over them. Here you go. You can pass them. Okay, so that's basically what I'm going to go over. I'm going to show you, yeah, I wanted to show you guys one more arc flash. Okay, this is a study for our campus at Dunwoody. Real study, and through the same system. We have a 750 kVA transformer, the terminals. You have a category 0, but the one that I like to always pick on, you can see here's a lot of category 0s, guys. When you get into the 480, you can see the 480 here. You can get into category 1 and the arc flash boundaries. Look at this. That's my favorite. What they do at the basement at Dunwoody, they have they're using the 6 disconnect means. Remember how the code allows you to have 6 disconnect in one location, no main? Now imagine if you want to work on this piece of equipment that does not have a main. There's no main on it. So between you and the wrath of Excel, when they push the energy into your chest, there's nothing other than copper, no fuses. So they can push, and the fuses are on the primary side of a transformer. Look at the arc flash boundary, 347. It's dangerous. The touch and the limited, these are just for the touch. That's okay. You can limited approach 42, typical, restricted 12, prohibited 1. These are the shock hazard. But the arc flash hazard, 153 calories per centimeter squared. So there is no PPE, and that's at the 6 disconnect means in the vault of Dunwoody at the bottom, and no main. So what does that tell you? If you were to go, typically, even if you open a panel to change a fuse, you cannot open because you could arc, right? Changing a fuse there, you can't. How are you going to disconnect? The only way you can disconnect this piece is you call Excel. You have to disconnect. There is no main. So that's one advantage, guys, of having a main for your building, is you can shut down and you can minimize this amount. So that's kill a lot of princes. Do you know about the story there? Are you saying? We killed an apprentice. Unfortunately, we did. One of not us, but you guys remember People's Electric, the accident that happens at People's Electric a couple of times ago? That was one of our apprentices that worked there. He was a 3rd or 2nd year apprentice with them. and they're working, what is it, 3,000 amp. I think they were adding to a 3,000 amp switch gear, energized, no PPE whatsoever. And I think they were climbing, my understanding, he was climbing under the switch gear to tighten things, no PPE. A kid, and it's not his fault, the fault of the, based on the state of Minnesota, whose fault is if your apprentice does something wrong? The journeyman, with them, right? That's why you guys are being tortured by Chad today for 8 hours, and yesterday by Paul, because you are worth it. You're responsible, right? So anyway, Torquay Ark, I think, faced the ground, a big ball of fire, and he died. So this is serious business. Another story happened at the Mall of America. Did you guys hear about the Mall of America a couple of months ago? I don't know if any one of you guys were involved in that. Maybe I should have. So the guy who also worked there is one of our apprentices. He told me his supervisor asked him to go thermal image the logs in a couple of panels. Now to thermal image them, you have to open the cover. That's an easy job, except no PPE. You're working there, you do PPE. When you open a panel, you have to put the PPE, the proper PPE on you, because you could drop something. Well, he wasn't wearing a PPE, opened a couple of them. One of them, accidentally, he dropped something, or maybe the edge of the panel went right and grounded it. Long story short, ground fault. Arc flash, burned his face, his neck, his hands. A couple of months in the hospital. And it was a Sunday, non-supervised. His supervisor wasn't there. So talk about, so working on energy as object, I don't know how they solved it. I don't know how OSHA did that issues, but so working, guys, in arc flash is a big deal. I can mess around with 240/120, but when it comes to 480 and three-phase, I usually kind of get scared, and I put my PPE no matter what, man. Okay. So that's a couple of arc flash. Did you guys get the stuff that I gave you? No? Is it going around? We have some handouts that's going around here. All right. I kept you awake for the most part. That's good. On a Sunday. On a Saturday. Well, after you do Saturday and Sunday, they get mixed up together. Okay, so we have a few things, guys, about the overcurrent protection device for you, and then I'll get into the short circuit calculation. Disclaimer. That's we have. I may mix a slick. This disclaimer, guys. So if you need smarter people to give you advice, don't come to us, basically. We're not the authority. Yeah. So when I gave you that sheet, don't show it to the inspector and say, if you want my professional opinion, I have to put my stamp as a registered engineer on it. Everything else is just we're chatting. Did you guys see they put the disclaimer in the NEC code book? It says use it on your own. So you guys are making it a law, and I'm going to use it on my own too. So if you did it right, because we're smart. If you did it wrong, it's your fault. That's kind of all the books, every book that you do, because we like to sue each other. So, okay, tab rules, overcurrent protection device location, installation needs, overcurrent classification, and fault current calculation. That's what we have, guys, for you. You guys use the tab rules? A few tab rules, yeah. So that's what we're going to be doing. Overcurrent protection device location, installation, classification. Location in the circuit. Overcurrent protection device, guys, location. Like I showed you, the code require you, with some exceptions, to put the overcurrent protection device, the fuse or circuit breaker, ahead of the feeder. Not in the middle of the feeder, not at the end of the feeder, with a few exceptions, tabs. So here's the panel, and here's the feeder that's going to the second building. I put a fuse disconnect here, take my feeders and feed the second building. By the way, that's not always the case in the high voltage systems. When you have a high voltage like utility type, the only thing that you're really concerned about is the short circuit. So not the load. So technically, I can have 100 amp fuse connected to number 1 conductor and tapped from it number 14, as long as I can prove that the number 14 conductor under short circuit condition and ground fault condition will survive that condition. Basically, it's not going to melt. So there's a lot of, when we size guys for high voltage, we size, are they going to be able to handle the short circuit and ground fault or not? That's the decisive factor. In the low voltage, the decisive factor is really the load. Are they going to handle the load, the full time load or not? So right ahead of it, this is a few rules, guys, about the 10-foot rule. Anybody use the 10-foot rule? 10-foot rule. When you use the 10-foot rule, it's really straightforward. I'm going to summarize it for you by a little graphic here with my graphics. Here's my let's go tab a 400 amp, right? Here's my 400 amp feeder. And oh, by the way, this tapping conductors is the poor man's way of doing business. I know you guys like it as contractor. The best way to do business is feed it from a separate feeders, because if you have a short circuit in any location, you minimize the interruption. So here's my feeder, and I'm putting my is the color? The color is hard. Sorry, that red is not the best. No problem. We can. Don't blue, yellow. Yellow would work. Okay. How about this? Perfect. Okay. Here's my circuit. Here's my gutter. Here's my 400 amp circuit breaker, and I need to tap this 400 amp circuit breaker. So I went here all the way to a fuse disconnect right here, and here's my fuse disconnect. Put my fuses in it and tapped it, and I'm just gonna go and tapped it with a motor here, and the distance from here to here is a 10-foot. That's what the 10-foot tab, right? So why it's so important, guys? Because they're cheap, 10-foot, and then I can tab another one from here, and a third one, and a fourth one. That's the most important application of that baby. And you keep tabbing, right? And what does tabbing means? You take the phase A and you tab through it to a log, and you go no overcurrent protection device. So that's your tabs. If you were to do this, if you were to do the tabs, there's a couple of rules. Number one, these conductors right here have to be protected in a conduit. Put them in a conduit. Number two, they have to protect it based on the overcurrent protection device. So the conductors have to be protected by their ampacity. So, and the one I want to start with is the minimum conductor that you can tap from a 400 amp is 1/10. So what's 1/10 of 400? 40 amp. So this conductor cannot be less than 40 amp. And since this conductor, what's 40 amp? That will be under 75, that will be number 8? Number 8. So that conductor cannot be smaller than number 8, period. So that conductor cannot be smaller than number 8. Cool? And since this is a 400 amp, you can take advantage of the 400 amp, the rule. You guys everybody knows the 800 amp rule. Up to 800 amp, the ampacity of the conductor can be slightly less than the overcurrent protection device. So I'm going to take advantage of this and make this is for 500 kcm. Cool. I have a 500 kcm. 500 kcm. The 500 kcm, guys, can carry 380 amps, right? Under 310.15b16, column 75. So why can I put a 400 amp on it? Because the rule says up to 800 amps, the conductors can have a little bit of ampacity lower than the circuit breakers, as long as the circuit breaker is the next standard. Okay, so anybody disagree that a 400 amp circuit breaker or fuse feeding from a 500 kcm, I'm tapping the 500 kcm into a number 8 conductor, right? So why number 8? Because you can't tap less than can I tap number 12? No. Can I tap number 4 out? That minimum is number 8. And the only condition, guys, is here. Let's make it easy and make the fuse as an overcurrent protection device and a circuit breaker. So what size fuse can I put right here? Maximum size fuse that acts as an overload and a short circuit here, 40 amps. So that's another condition. So if you are to tap from a conductor The conductor cannot be less than 1/10 of the overconduction device. It has to be enclosed in a conduit, protected. It has to land on an overconduction device that rated based on the ampacity of the conductor. Done deal. Any comments, guys? Any questions about that? So that's so you can do your math now. If you have 1,000 amp feeder unit tap here, multiply by 1/10 of that, it'll get you 100 amp. The minimum is 100 amp. The other condition is you can't move this disconnect further than 10 feet away from this gutter. Otherwise, that's not a 10-foot rule. Any comments, any questions?
Yeah, one of the problems that I found is people will set a disconnect switch 10 feet away. The problem is the code states that the length of the conductor shall not exceed 10 feet. So from the actual tap, physical tap to the top of that disconnect switch is where the 10-foot is measured.
From the conductors, absolutely. And so you're looking at, if you measure from here to the disconnect, you probably have to add another 6 inches here, another couple of inches here. So when everything is said and done, you're really looking at probably 9 feet between enclosure to enclosure. That's why I always say, when everything is said and done, the enclosure to enclosure, because when you measure, you're not going to go to the terminals. Enclosure to enclosure, you're looking at 9 feet. Good point. To the enclosure of the disconnect. Now, how far can I go from this fuse all the way to this equipment? You guys are cool. No limit on that. Any comments, guys, about this tab rule, that 10-foot tab rule? Do you take advantage of it? Yes, no?
But you wouldn't put 10 feet on there, but typically it's a 10-foot.
Yeah, and this is, I'm going outside. A lot of times, guys, you stay inside the same enclosure. You stay inside the same enclosure. I put the 1/10 here because I'm moving outside the enclosure. Okay, so that's basically what this rule is, and the field insulation. So if you look at the ampacity of the tab conductor is not less than the combined calculated load on the circuit supplied by the tab, not less than the rating of the device supplied by the tab, and so forth. That's what we get. And if you go outside and wire it in the field, this is where the 10% came to be. Any comments, guys? Anybody's excited about this rule? No?
What's the article on?
That would be 240 dot something. Everything is in 240. What's the tab? 240 dot, it should be here somewhere. You ask our question, man. Here, 240.21. I know it's dot something. 21. Okay, let's go to 25 feet. 25 feet is even easier. 25 feet, guys. Here's my conductor. Let's take the same conductor. Can you guys see the color here? Okay, so let's go tab it. And that's a poor, when I say poor man's job, when I don't pay for the cover, so probably that's a problem when you don't pay for things. So you put, here's your fuse, here's my disconnect inside it, and here's my equipment, machine, panel, you name it. The distance here, from here to the conductors, let's be very specific here, is 25 feet. So that's condition number one. You can't be 25 feet. And like we said, probably end up with 24 anyway between enclosure to enclosure. Okay, what's the rule? Let's go tab a 600 amp. Make it easier. Here's my 600 amp. Or you know what? Because we already tabbed a 400, let's just continue with the 400. Let's tab at 400. So the code says, guys, the conductors here cannot be less than 1/3. So what's 1/3 of 400? 1/3 of 400 is what? That will give you 320. What's 1/3? 133. That's what I'm looking for. 133 amps. Now, can somebody go get me a conductor 133 under 75, guys? 133 amps. That's hard to see. 133 amps. Anybody? What's the conductor size? More than number one? 1 aught? 1 aught. So the conductor size cannot be more than 1 aught. And, okay, 1 aught. So 133. What's the fuse size here? You don't go up. You have to go down. What's the lower size from 133? Thank you, 125. That's another thing. When you tap conductors, you can't go up on them. So I have my overcurrent protection device has to be 125 because I don't have 133. What happens if you don't have a standard circuit breaker of use? I always say you custom design one by busman. You have to give him one of your legs and an arm with it, or you can go down.
That 125 is the maximum, right? You're sizing that fuse up below, right?
Yes. Yeah. Everything is this is the minimum conductor, and this is the maximum overcurrent protection device.
You can't put a bigger conductor and then put a bigger fuse.
You got it. You got it. Absolutely.
Well, that guy made his own yesterday, he didn't have much to do.
Yeah, what about those common pipes?
The what?
That was copper pipe with plastic.
See that?
Depends on where you get yours on Paul's video.
Ah,
I'll show you that.
it's I remember with the fuses, we used to tamper with them and put the pins in them, so they don't trap.
This guy just took copper pipe and just put coloring on it and
Stuck it into it?
With blades. Color tape.
Yeah, and just stuck it in. No, I haven't seen that one. Wow, there's a lot of crazy stuff that you do, and you know, for the most part, unless you have a ground fault and short circuit, it could live forever. But if you have a short circuit, you blew up something. You know, this is no worse than somebody drinking and driving, right? You see, the people do it all the time. Why do you pick on electricians, man? So here is you tap your feeder. You tap it with whatever hardware you use with them. So looking at this one, guys, if that was a 100 amp, what minimum with overcurrent protection device do I need here? Maximum 10 feet. If this is 100 multiplied by 10, the maximum that you can put right here is what? 1,000. Because you take 1,000, 1/10 of 1,000 will give you 100. Here's the fuse 100, the conductors are 100. So you covered these. Now if you put 200 here, you just basically have a bigger conductor. So that's your conductors. Feeder tab 25 feet. We talked about the rules of feeder tab. Each set of conductor feeders separated required to meet the requirement of, when you get a feeder tab like this, guys, with conductors, that was changed in 2011. Now, the same thing, you will have, when we tab for transformers, there's a rule that says this cannot be further, primary and secondary, between the primary and secondary, both the primary and secondary cannot be for more than 25 feet. That rule, 25 feet or 10 feet. So if you put your panel 10 feet from the transformer, you don't have to have an overcurrent protection device right at the secondary, and you can depend, as we always do, on the secondary right here, the panel main to be used secondary overcurrent protection device. What are the rules though? Anybody remember the rules? So let's suppose that this was 100 amp. Let's take 100 amp here. This is 100 amp, and this was 200 amp. So what do you guys think the conductors here have to be minimum? Anybody? No, this set. Is the color okay? 100 amp. So what do you think this conductor set minimum have to be? 200 amp. They can't be less than 200 amp, the load at the end of it. Now, here's the issue here. Here's my overcurrent protection device in the second panel here, right? You have to have an overcurrent protection device. So what size overcurrent protection device are you going to have here to protect it? Maximum. The problem is always a maximum. Yeah, well, but there's issue though. There's voltage ratio. So yeah, you have to ratio it. You're absolutely right. If it's 10 feet, you have to ratio it. Here's 480. This is primary 480, right? Secondary 208. Secondary 208. So what you do, is you take the voltage ratio, which is 408, right? Not 408, 208, Chad. Here's the 208 divided by 480. That's a voltage ratio to transfer the current to the primary, right? The higher current, and then you multiply. So this is, and then you multiply this one by 100 because this is the smallest, right? Why did they choose 100? Because it's the smallest conductor. Okay, and then you multiply it by 10. Let me go over this one more time. That's a 10-foot rule. So you divide by the voltage ratio because the current here is not the same as the current here. There's a voltage; it's going to be lower, right? So you have to convert the current from one voltage level to another voltage level. That's easy. You just divide it by the voltage ratio, multiply by the voltage ratio. Can somebody has a calculator, guys, do that? So take the voltage ratio, multiply it by 100, because that's how much 100 the secondary is. That will get you the current on the primary right here. Okay? Then that current cannot be 10 times, the overcurrent protection rate cannot be 10 times the current that's here. Okay? So what's that? What would that give me? Anybody has a
433?
433 altogether?
Altogether, the whole thing.
Okay, 433?
Yeah.
That's sounds too high. No? Is it? I need a second, guys. You can't, like a selection, you have to have second. 433? Okay, 433. It is. So I can't go up, so what do I need to do? What's the next standard down? 400. 400 amp. Now remember, this is the maximum. This doesn't mean it has to be 400. This is the maximum that you can put here to make sure. Now, can I go and based on the size of the transformer here and put this one 200 amp? Absolutely. Everybody understand? We'll look at each other. You lost it? This is the maximum that you can based on the tail, the conductor tails.
Isn't that always kind of going to be the case, though? That the primary breaker is always going to be below the maximum.
Absolutely.
You know,
Yeah.
So you never really need to calculate that.
Well, here's where you need to pay attention to it. If
There are
you're
more than 2 panels there.
well, take this. If this transformer is here, and this panel is 100 feet away from the transformer, can you do that?
No.
10 foot.
Yes. That's the only thing is you have to keep. Yeah, if you keep the 10-foot rule from the transformer, you almost always the primary is
Well,
always.
if that panel's 100 feet, then you say it's disconnect here. Right?
Yes. Yes. So if that panel needs to be 100 feet away from it, what do? You go right by the transformer, we'll let you fuse disconnect, and go all the way to the 200 feet. So the reason why I guys put it on, took the smaller, because that's the worst scenario, right? Smaller is the worst scenario. If it's good for the 100, it's definitely good for the 200.
There's no way you feed a 400 amp and final going 300. 480 in, 208 out.
No, that's the maximum.
What's what we're just saying? This is the maximum.
The maximum.
Yeah.
There'd be no protection.
The maximum to protect. That's the maximum to protect this cable. The maximum to protect this cable.
Code doesn't let you go that high anyway.
Yeah. When you size the primary with the transformer, what do? You're going to take the full load amp of the transformer, multiply it by 1.25, and then you size your primary, right? So that's what we typically do. If you are to adhere to these rules, that number that you came up with cannot be higher, and I hate to throw numbers here, that number here cannot be higher than this ratio, basically. This ratio. But here's a challenge. What if it's higher? What if you need it higher?
Maybe you're feeding 4 panels or 5 panels.
Yeah. What if you need it higher? What if it needs to be higher? What do? You just put a bigger conductor here. You know what I mean? If it needs to be higher, what do you do here? Instead of whatever 100 amp cable here, you can put a 200 amp cable to that panel, if that makes sense. So that's That's a few rules about the transformer secondary conductors. Tabbing the conductors. And we talked about, guys, conductor tabbing conductors. Rounding up, you cannot round up with conductors. This is one of the most important things. So here's my question for you. Can this be a 400 amp and this cable is 500 kcm? Can this circuit breaker be a 400 amp and this conductor be a 500 kcm? No. Why? Because 500 kcm can give you 380. Because it's a secondary of a transformer and there is a tap rule here. In any other location, that would be perfect. In any other location, if it's not a tap location, that would be completely legit to put a 500 kcm to feed a 400 amp circuit breaker to protect a 500 kcm, except if there's a tap rule. A tap rule like we showed before, or a secondary of a transformer, because these guys are not protected at all. The only protection for these conductors from this point all the way here is where? On the primary side. On the primary side. Okay, so that's your so we talked about the 10-foot roll, guys, for the transformers. The 10-foot rule. So transformer secondary tap conductors cannot be less than 10-foot rule, but you have make sure that 10% shall not exceed the ratio. Here's the primary to secondary ratio that we just talked about, and we converted them. The primary to secondary ratio. So 10 feet. So let's take one of them here. Let's just take. So I'm going to make this one, guys, a 400 amp. 400 amp here. Okay. My conductor, I know for a fact, here has to be more than 500. So I guess what's going to be 600. Okay. 600 amp. Okay. So the primary for this conductor, and I'm going to go to the max. Oops, we're not coming in here. So that one, and let's just make the system symbol. Let's make primary 600 and secondary 240. Is that symbol? Now we complicate things even. Talk about engineers, huh? 240 divided by 600, right? 600 multiplied by. Now, what would you multiply by here? Well, 600 kcm though. Multiplied by. Well, typically the ampacity of the conductor. So the ampacity of the conductor are actually going to be more than. It's going to be more than 400, right? The ampacity of the conductor. What's the ampacity of 600? 400 something? How much? 420. So you multiply this by the ampacity of the conductor, which is 420, because that's what you're protecting, right? 420. And what would that give you, William? How much? 168? 168? 168 amp. Okay, so what would that be then? You can't go higher, so it have to be 150. There's nothing between them. Oh yes, thank you. You multiply by 10. I'm sorry, thank you. 110, so that will give you 1680. 1680. Yeah. Now you're gonna look at me and laugh, which is not how much you're gonna put. That's how high you can go without exceeding. It's ridiculous, guys. I know it's ridiculous because you can't. You would never put something like this. So that's where you typically don't have a situation like this. You don't have a situation. Any comments, guys? Any questions?
Where did you get the 420? Again, it's the ampacity of what size?
The ampacity of the 600. The 600.
Okay, it's not 600 amp. It's 600.
600. I'm sorry, kcm.
Oh.
This is 600 kcm. kcm. Any comments, guys? Any questions? Did I confuse you a little bit more? So that's the ampacity of your conductors. transformer secondary conductors. 25, this talks guys about 25 foot rule for industrial secondary conductors, not over 25. Here's what the rules for them. Condition, first of all, we are in an industrial installation. Only qualified people like yourself working on the system. Here's the condition. The ampacity of the secondary conductor is not less than the overcurrent protection device at the end of it. All overcurrent protection devices are grooved. The secondary conductors are protected from physical damage. And I don't think we have any, we don't have any limitation. In a case like this, we don't have industrial. Again, qualified people, there is no limitation on the ampacity of the conductors. No limitation, even the ampacity of the conductors. No relationship between the overcurrent protection device ahead of them and the conductors. Again, special application for 240.21 for industrial installation. So really, if you have a transformer industrial installation, you can take, technically you can take number 4 out and go feed a load from it within 25 feet from it without worrying about what the primary of that transformer is. As long as you stay within 25 feet of a transformer, number 1, and number 2, as long as at the end of the conductor you put a circuit breaker to protect that conductor based on its ampacity. So based on its ampacity. It gets even interesting if you have outdoor transformer secondary building or structure except at the point of load. The conductor is protected from physical damage, so you can, do you see any limitation how far you can go outdoor? That's what I see. You can have, if you're doing things outside, like overhead conductor outdoor, you're only concerned, really, when you tap conductors, is not the overload. So let me have a ridiculous, oops, here you go. So with transformer, conduct transformers, where are we here? Outdoor. Okay, we got that one. Transformer, outdoor conductors. So I can, if I'm pulling things outdoor, guys, I can have a conductor here, and no limitation. I can tab a load here from this conductor. I can tab another load. Everything is outdoor, right? And I tab another conductor from here, and I can go in the transmission. The only limitation, guys, you're going to see if the short circuit right in here, you need to make sure if you no limitation in distance, that short circuit, circuit breaker must be able to protect the feeder as well as the tabs from short circuit and ground fault. So only limitation. I can have number 14 here with 15 amps. I'm limiting the load to 15 amps with number 14, no problem, and I'm outdoor. If I have a short circuit in a number 14, I would make sure that the circuit breaker will trip fast enough before number 14 melts. How do you do that? You do it by something called damage curve for conductors. Every conductor, guys, every conductor have 2 ratings. Anybody have heard about the damage curve for conductors? You heard about the damage curve? There's the conductor. So when take 400 amp kcm, I have a 400. Let's just say 500 kcm conductor. 500 kcm conductor can carry 380 amps continuously forever, right? But how much current can a 500 kcm carry? Short circuit current, and for how long? That's the damage curve for the conductor. And actually, I have one here. When we were looking at the system, I don't know if I just did not want to go there. Let me show you one of these damage curve for the air handling unit. If you look at the air handling unit, can you guys see that conductor here? Not that one here. Oops, there you go. That black thing. That's a damage curve for the conductor. So here's my damage curve for this conductor. Single phase. This conductor, that black thing, can carry 75 amps. 75 amps forever. Now what happened is, if you go down here for a short amount of time, you can carry, here's 1,000 amps, 2,000 amps, 3,000 amps, 4,000 amps, 5,000 amps, 10,000 amps. This conductor can carry 10,000 amps right here for how long? For this is a 0.01, this must be 0.02, for 0.02 of a second. Same conductor can carry 10,000 amps. For how long though? For 0.02 of a second. That's called the damage curve of the conductor. Okay, so make it even more interesting. Let's look at the 1,000 amp here. Go all the way to the one. How long can this conductor handle 1,000 amp? All these are short circuit conditions, abnormal. Take this, here's 1,000, go all the way up until you hit here, right here, okay, right? Everybody's okay with that? So if you cross-reference it here, it's between 1 and 2, say 1.5 seconds. For 1.5 seconds, that conductor that carries 75 amps can actually carry 1,000 amp for 1.5 seconds. After 1.5 seconds, guys, if the circuit breaker does not trip, what's going to happen? Vaporize. That's the word that we like. Vaporize. Vaporize. So that conductor is going to vaporize. So that's basically what the damage curve for cables.
Is that blue curve protecting that, or which?
This is that conductor. Oh, the conductor that protects it right now is the blue curve. Now look at the blue curve. I want you guys to cross-reference the blue curve right here. Now what's right here very clearly the black curve is going to protect it, right? Because if you have a short circuit anywhere in this area, the circuit breaker will trip before you reach the damage curve. Clear? Mm-hmm. Now what's going to protect it right in here?
No.
Hold your horses. This is an air handling unit. What do you have with the air handling unit? What do we have for air handling unit? Overload. Thank you. So what's going to protect you right at this level here, right from just that little thing here, we're not showing, is what's going to protect you is the overload. Because that's an air handling unit. And air handling unit, what do they have? Overload. And your overload is set 20 seconds or so forth. So right in these levels, the overload would be able to protect it at these. And that, but you want the breaker to, it will trip, but you will trip fast before the conductor catch fire. So that's why that conductor, by the way, was way oversized. That circuit breaker, remember how we moved it? I think it was 125, and we have to move it, we moved it down here. This is how it should be. That circuit breaker, that's how it should be. We shifted it way too far, and I told you that's the safest. Now when you sit it here, see that little thing here? That little knob protection here, which one is going to protect you here? That will be the overload. That little overload. So every conductor has two values. Damage curve, continuous amp rating, can run forever, and damage curve rating, which it goes, the faster the circuit breaker trips, or the higher the current, the higher the current, the faster the conductor is going to melt. Any comments, guys, about this one, the damage curve for conductors? Just a side note, when Excel, and you guys jump with them, when Excel and all the utilities do size transmission distribution system, the major decisive factor in the size of the conductor is not the load, because at 69,000 amp, 69,000 volt, the amps is not an issue. The decisive factor is a voltage drop because of the thousands of miles of distances. That's an issue, right? Voltage drop issues, and the short circuit issue. And so it starts with voltage drop, short circuit, and then the full load. That's for the high voltage. For the low voltage, it goes the opposite. We start with the full load. That's what we care about. I want to carry the full load, and then the voltage drop, and then the last one is short circuit in the low voltage system. I'm sorry. Any comments, guys? Any questions?
Besides the conductor rating system.
You size the
System contingency first and low second.
We can put capacitors on the line and keep the voltage. We don't size conductor for voltage.
You size based on the
load.
On the load.
Load and the losses.
The short circuit. Don't you size based on the short circuit?
Basic running load. And then the contingency, so if there's 2 or 3 other lines out, and they still want to keep them in unity, there's usually the contingency loading drive.
So when you guys bring a feeder from here to Minneapolis,
There's usually more than one path.
don't you worry about the voltage drop in that?
You do, but.
You have a, yeah,
but you
your
can take
system
care of
is-
that with capacitors and transformers.
Yeah. But that will correct the
Bars
power.
do not travel well on the transmission line, so you'd never
Yeah.
decide to send bars down the end of the line. You
Yeah.
just put the bars down there.
Yeah.
Just like-
But the capacitor will correct the power factor though. You still have a current going right through the conductor, right? It's going to get you a voltage drop.
Right, but the current, the everyday current is far less.
Far less because the voltage is so high.
It's far less than what the conductor can actually carry. The maximum current is dependent on system emergency.
Okay,
In most areas, there's more than one transmission path.
gotcha.
You want to be able to take 2 or 3 other circuits out, still carry the load so they can work on for the storm. We don't want the whole area to go out.
Gotcha.
Not-
Reliability and redundancy. Gotcha, gotcha. Okay, any comments guys about the damage curve though? Any comments about the damage curve? Do you guys run damage curve at Excel for the cables when you run them? Do you use damage curve for your conductors for underground? Do you run the damage curve
Underground, different animal.
underground?
For
Yeah.
overhead, it's meltdown.
Yeah. Yeah. But you have a software that do through the calculation for transmission lines and okay. Any comments, guys? Any questions about that? Comments? Okay. So that's my outside conductors. Secondary conductors not over 25. We talked that one. Transformer secondary conductors. All right, we'll go into that one. Moving on. I'm sorry. Is that? You guys are having a.
I think they need a break.
Need a break? Is it break time? Yeah. Okay, let's have a break. That's a good timing to have a break. Okay, let's have a break.
Good one, Matt.
Oh, you helped me along.
Wow, that's awesome. So what is that?
I got a situation. Okay. Service I put in. After I put it in, I realized it was an issue. I didn't catch it. It started and the inspector didn't catch it. But I basically got a double lock meter stuck in the house. So I went back to the house. I go to the 3 wires. Okay. New fields are 2 cross. Okay. I established the ground in the garage.
It's a reserve system. I mean, it's a reserve. Yep.
Now I also got a couple of pipes.
Okay.
These are but now, am I creating a path here for neutral point? Because this is, one of the main service too.
No more than your neighbor and you creating the current path. Look at your neighbor and you.
Yeah.
Right? Your neighbor is connected to, look at 2 woods side by side. Aren't you guys connected to a copper wire in the city? Right? Exactly what's the difference?
The only difference I could, the only difference I could see is that if there were dimensions, the copper point is still grounded, but my only return path is in the neutral ground.
That's the old system. And every building is wired like that all over the place for decades.
It is, yeah, no, that's just fine. It's just that I've got a house with a copper.
Same thing,
Yeah.
still there.
But this is a service though. You are right on the line side of the disconnect.
Yeah.
You're not inside the building. You're providing two services for
Two
meter.
separate
Two
services.
separate services.
Two separate panels.
I don't see any issues. That's no difference than having two buildings and the same thing tied together. So the current is going to try to chase into the transformer, the source.
Yep.
So it's going to have through the copper here,
Through the ground here.
and through the ground, and here's another path through the water. And like I said, that's no difference than you and your neighbor being tied to the same water service. Yeah. It's going to go the same thing through the water service all the way back. But how much though? Take a nicely sized neutral here, with all this. So this will be short compared to this, but that cover also could be shorter. I can see some good current here going through it.
Yeah.
Yeah.
Just normal.
There is no violation of the code. No, definitely not. And actually, the code says if you have water, you have to bond through the water.
You have to, yeah, the water has to be bonded so that they do get a short insight
Yeah.
to the water.
Yeah. And if you lose your neutral here, now you don't have open neutral system. Right? You don't have an open neutral system. If you lose your neutral here, you don't burn equipment here because your system is grounded through the earth, as well as the cover. But the challenge that I heard is, problem is our current going through the water is creating holes into the water system, the cover system, electrolytes and all this good stuff. And so that's a water issue,
Yeah.
not an current.
But that should only be DC. What causes AC should, it should come off and come back on and come off and come back on.
Yeah. So that's the only, I don't see anything wrong with that.
Okay.
Yeah. But I see your point where it's a cover bar going between and there will be some current.
Yeah, there'll always be some neutral current flowing in there. Whether that's an issue or not is not obvious.
I wish I brought that book for you guys. That my knowledge again from the voltage drop is from my textbook that I use. They always say the sizing that I told you is short circuit and voltage drop as you move miles and miles and miles. So the load might be 5 amps, but that 5 amps going thousands of miles, or not thousands, but hundreds of miles, even 100, probably 20 miles in the distribution system. Yeah.
No, I'm a transmission engineer
Okay.
myself, so I transmission lines are what I do.
Okay.
All those are sized on amp capacity, how many amps
On the
can be
system.
down the line. And voltage, we correct auto transformers or with capacitor combination voltage. So voltage drop is, you have to consider what you're going to. And the high voltage isn't very much.
The capacity cost and minus one minus two condition.
Which was all N minus two.
We're always operating in minus one. Yeah, on the distribution side too, we don't think we ever look at damage curve.
Yeah.
We do want to look at damage curve on transformers. You know, we look at-
Yeah, that's always
I do underground transmission, and we're very careful. Those are huge,
They do a damage curve in them?
more than a damage, very, very transformers. No, an underground transmission.
Oh, the underground, yeah,
Oh, yeah.
Well, very careful, intricate analysis of short circuit calculations and emergency ratings and impedance of the system and the transformers. Heating of ground, heat dissipation, where it gets to be a fairly nasty, finding out an analysis. You come up with that cable reading.
Hard to get them back.
So, 2 weeks ago, I went to a conference on gas use limits in here.
Hope you guys want to start building here. I'll scan it. Okay, guys, my friends. My friends. Okay, guys, everybody's here. Hello. Should I shout them?
It's a little thin right now.
Whistle.
Everybody who's in here is here.